Hello everyone, I'm Dr. Sina Shamekhi and this is the second lecture of the Bioinstrumentation course, Basic Sensors and Principles. As I mentioned before, transducer is a device that converts energy from one form of energy to another. Sensor converts a physical parameter to an electric output, and an actuator converts an electric signal to a physical output. In this course, in this lecture, three types of measurement will be discussed. The first one is the displacement measurements. The second one is the temperature measurements, and the third one is the optical measurements. In displacement measuring systems, we have two main purposes. The first one is the measuring some parameters. As you can see, the physician and biomedical researchers are interested in measuring the size, shape, and position of the organs and tissue of the body. And variation in these parameters are important in discriminating normal from abnormal function. As a second purpose, we use these measurements to make some decisions about the normal function of the organ or whole body. Based on the location of using those sensors, we can divide the displacement sensors into two categories. The first one is direct and the second one is indirect. For example, for direct one, determining the change in diameter of blood vessels and the change in the volume and shape of cardiac chambers directly. And for indirect measuring, for example, we can use some secondary parameters to quantify movement of liquids through heart valves. And for these types of measurements, we will use four types of methods. Four methods. The first one, resistive methods. The second one is the inductive. The next one is capacitive. And the last one is the piezoelectric sensors. We have various types of resistive sensors, but as the simplest resistive sensors, we can use potentiometers to measure the displacement. These potentiometers produce a linear output. As you can see, we have three types of potentiometers: the linear translational, single-turn, and multi-turn. The first one, the translational linear potentiometer, can be used as a simple displacement measurement system. Suppose that we have a drive voltage here, Vi, and we want to use Vi out to measure the displacement Xi. If the total length of the potentiometer is L, the output voltage can be measured as this equation. You can connect this tip to any moving object, and you can use this tip to measure the displacement Xi. But the measuring parameter in this potentiometer is a translational type. But in the second one, single turn, we can measure some angle here. If the total angle of this potentiometer is 217 degree, the ratio of phi over this the total angle multiply by Vi will generate a voltage V out here. And now, based on the output voltage, you can measure the angle here. And in the third one, multi-turn, you can measure the angle, also the depth. The angle and the depth. You have a helical path here, the helical path here, and multi-turn rotation of the sensor here leads to a complete measuring of also the length and also the angle. One of the main application of these types of the sensors, multi-turn, is to control the position of the table, for example, in some devices, for example, the table of CT scan or the dental chair or something like this in ball screw position controlling. The next main type of resistive sensors is a strain gauge. Strain gauge is one of the most important sensors in the field of bioelectric engineering. As you can see here, when a fine wire, a thin wire, a fine wire is strained within its elastic limit, the wire's resistance changes because of change in the diameter, length, and resistivity. We have a wire, for example, here you can see, and if we strain this wire, the volume of this wire will be constant. But because of this new shape of the wire, the diameter of the wire will be reduced and the length will be increased. If we use metal in a strain gauge, the resistivity will be constant. But if we are using semiconductor, the resistivity of the material will be changed. Therefore, that parameter should be considered in our formulation. Measure extremely small displacement on the order of nanometer are achievable using this type of sensor. Let us start to solve the equation and find the last equation of the gauge factor. This is your first exercise homework. You should start from here and you should find the last equation in the next slide. Let us start from this equation, and at the next slide I will tell you about the homework. You know the main equation of resistance is this: R equals rho multiplied by L divided by A. Rho is the ohmic or resistivity, ohmic density or resistivity. L is the length of the sensor and A is the area of the wire. After a differentiation, you can find this equation, and if I divided this equation by R, you can find this equation as a differential equation. And as you can see, delta R divided by R equals delta L divided by L minus, focus on this signs, minus delta A over A plus delta rho divided by rho. I rewrite that equation: delta R divided by R equals delta L divided by L minus delta A divided by A plus delta rho divided by rho. We should find the relation between delta R divided by R divided by delta L divided by L. It means that we should find the variation of R because of the variation of L. Because we want to measure the displacement. We want to measure the results of the displacement as a variation in the resistant value as the gauge factor. Therefore, we should convert the variation of area to the variation of length. For this purpose, we should use the Poisson ratio mu that give us a simple equation, relation between the variation of the diameter and the variation of the length in a fine wire, in a material. A material, when we strain a material, the diameter changes are related to the change of the length. So you should use this equation to achieve this equation from this one. And as I told you in the previous slide, you should start from the main equation, R equals rho L divided by L, and write the steps, and reach to this equation. And after this equation, you can divide delta R divided by R by delta L divided by L to achieve this equation. Okay, this is your first homework. I rewrite the equation. Delta R divided by R equals 1 plus 2 multiplied 2 mu delta L divided by L plus delta rho divided by rho. As you can see, the first term is only related to the variation of length, and the second one is only related to the variation of the resistivity. Therefore, as you can see in the previous one, we call the first term dimensional effect, and the second term we call it piezoresistive effect. Dimensional effect means that this is related only to the dimensional change, and piezoresistive effect means that this part is related only to the resistivity change in the strain gauge material because of the pressure or strain or structure change. The first part, dimensional effect, is dominant in the metals, and the second part, piezoresistive effect, is dominant only in the semiconductor materials. As you can see here, the gauge factor was this. The gauge factor in metals, as you can see, these materials is low, is small, and also this, because the mu is small too, and the gauge factor of the semiconductors are large because the variation of the resistivity in the semiconductor materials are large. Therefore, the gauge factor for the semiconductor materials is approximately 50 to 70 times that of the materials of the metal strain gauge And also note that the gauge factor for materials is primarily a function of dimensional effect. For most metals, mu equals zero 0.3, and thus the gauge factor is at least 1.6 almost. Whereas for semiconductor, the piezoresistive effect is dominant. Based